So, good afternoon, everyone. Welcome to this first interaction session of Experimental Physics 2 course, which is being taken by Professor Amal Kumar Das from IIT Kharagpur, and I am Rinalini, PMRF TA for this course. These course interactive sessions will held it on every Saturday from 3 to 5 p.m. and this is the first session for this course. This is second module of experimental physics course that we had last semester also. It was experimental physics 1 and this is last time it was more about mechanics experiments and this time it will be more focused on quantum physics and optics related experiments. So okay, let's start today's session. So this experimental physics 2, as I said, will be dealing more with optics and quantum physics related experiments, but basically we'll begin with talking about or discussing about the basic analysis that is done while carrying out any experiment, like how to take the data, how to take care of error, how errors are added, what is significant figure in any value that we measure, how to calibrate instrument, how the results are interpreted, how the graphs are plotted, and what are the precautions we have to keep in mind while carrying out these measurements. So this is the basic thing that we had kind of already also discussed in experimental physics 1 course, but we will also do this in first 2 weeks, as you would have already seen in the lecture video by the professor, that we'll again go through these topics because this is very essential. Apart from this, in this course we'll get to know and about the basic components that we find in optic laboratory, like light source, mirrors. There are different kind of mirrors, different kind of lenses, beam splitters, prism, grating, etc. So in this course the experiments will be dealing with reflections, refractions, interference, different kind of bifractions are there, different way of polarization, like plane polarized light or circularly polarized light. Apart from this also there will be we'll be discussing several experiments on quantum physics. So as you would have already seen, this first week's lectures were revision of experimental physics 1 course. So we'll discuss that, and especially out of all the experiments that we had done last time, because your assignment 1 that you have to submit by 5th February, I think, in that I found that most of the questions were dealing with simple harmonic motion and oscillation and also error analysis. So I'll mostly focus on these two things in today's session. So this week, this week's lecture was, as I said, based on last experimental physics 1 course. So let's start. So what these two things, the two things that are focused in the assignment also are error analysis and simple harmonic motion. So let's start with error analysis. So whenever we carry out any kind of measurement, even inside lab or outside lab, whatever we measure, that value has some uncertainty in it. Like say, if I have a random stick or rod, and I am trying to measure it with a 1 meter, say 1 meter ruler I have. I'm trying to measure. Then this ruler, it has its least count, you know. That least count could usually is like 1 millimeter. So if I'll measure the length of this rod or ruler, there would be error of plus minus 1 mm, whatever value I'll get. Say if I'm getting 200 millimeter, then I cannot get accuracy less than this. So this is the least count. Either it could be 201 mm or it could be 199 mm. That I'm not sure. So that is I'm not certain about this measurement, the value that I'm getting. So this is called the uncertainty, or also we can call it approximation. Because I can tell that the value is 200, but it's not 200 mm, but I'm not certain about it. It has error of plus minus 1 mm, which we are getting from the least count of this instrument that we are using. So we had discussed about more of the screw gauge, vernier caliper, these things in experimental physics 1. If you want to guys want to watch that, the videos are available. The professor's lecture videos are also available on YouTube, as well as this interactive session that we had last semester. Those are also available. So that I'm not going to explain in detail how we calculate least count, but what I want to focus is how the error comes into picture whenever we take any kind of measurement. So this is, now there are two aspects to any value, any measured value that we talk about. One thing is accuracy of that value and another thing is precision. Let's try to understand this with this picture. So accuracy we define as a measure of how close the measured value is to the true value of the quantity. Like say, if we know that acceleration due to gravity is 9.8 meter per second square, right? So if I am doing some experiment and using that experiment I find, say one student found the value to be 9.7 meter per second square. That means it's close to the true value. This I am calling the true value. This is well known fact that G is 9.8 meter per second square. One student conducted this experiment and he or she found the value to be 9.7 or 9.9 meter per second square, which is close to the known value. So we can say this is accurate. Another student, when they performed the measurement, they found the acceleration due to gravity value to be 9.11 meter per second square. Now as you can see, this value is far away from the true value 9.8 that we know, but it's giving us the result in up to second decimal digit. That means its resolution is higher, but so we can call it more precise because it's giving up to it's giving precise measure, or we can say second decimal digit. So this value can be called more precise because as the definition is here, its resolution is higher, but it's not accurate because it's very far from the true value. So these are the two aspects that we need to keep in mind when we are talking about any kind of measurement. So from this image we can see, like this is an example of low accuracy. Like this is some kind of dart and bolt kind of game where a person has shot these darts, and of course the target is to hit the center, but as you can see these dots are far away. So there is low accuracy as well as low precision. Here again our aim is to hit the center, and all these darts have hit it at near this region, as you can see, but they are all, I mean whatever 5-6 attempts the person has done, they all are pretty close to each other. That means they are highly precise but not accurate. Same way here, these are, every attempt is very different from the subsequent attempt. So this is low precise but high accuracy because it's closer to the aim part or the true value. For this example you can see here the accuracy is also high and the precision is also high. So in this way, through this analogy, you can understand what we try to mean to understand by saying that a measurement is more accurate or precise or otherwise. So this is the two aspects of a measured value. Now we'll see what type of errors are there in any measurement. So in general, the error in any measurement can be broadly classified as systematic errors or random errors. So systematic errors, I'll first read this out. So errors associated with each data throughout the measurement in the same way. These errors shift data in one direction, either positive or negative. These can be from instrumental errors or imperfection in experimental technique or procedure. Again, so these kind of errors also we had discussed earlier, so I don't want to talk in detail, but like these two kind of errors are there. And let's move to the calculation part which we need. So error, mathematically we calculate in three forms. One is absolute error, second is relative error, third is percentage error. So how do we calculate absolute error is, it is the magnitude of difference between the individual measurement and the true value of the quantity, that we call absolute error. Let's again take the example of g, acceleration due to gravity. The true value we are talking about here, true value is well known, which is 9.8 meters per second square. Now again the same example we'll take. One person has done some experiment in lab, and they found, or they calculated it to be 9.7 meter per second square. Then if we talk about what is the absolute error in this measurement, for that we'll subtract this measured value from the true value, or vice versa, it doesn't matter, because we take the mod of this difference. So either you can do this g minus g prime or g prime minus g. 9.8 minus 9.7, and we'll take mod of this, means it will be 0.1. So the absolute error will be 0.1 meters per second square, and as mentioned, this absolute error is always positive because we take mod of this difference. So this is one way of representing the error, because we can compare what we have measured and what is well known true value. There is another way to give the error for any measured value, which is relative error. In relative error, we take this absolute, it is the ratio of mean absolute error to mean value of quantity measured. So this mean, I'll explain why we are talking about mean in next slide. I have some example, but basically it's like the ratio of this absolute error to the true value. This is called relative error. And when we take percentage of this thing, that is when we multiply it by 100, then we get this error in form of percentage, that is called percentage error. So these are three different ways we assign error to any value. So let's understand with this example why we were talking about mean, why we were talking about mean absolute error or mean value here. So one term we were using till now was true value. This is valid for things that we know, like acceleration due to gravity, its value we know. But there are certain time when we are doing some experiment where the absolute or the true value we are not sure about. Like here is an example where the person is conducting successive measurement and the readings come out to be I think 5 times they have carried out, and these readings come out to be different. Here we don't know what is the true value, so we'll take mean or average of all these 5 values and consider that to be the true value. So here T1, like they have done the whatever was the experiment, they have conducted that, carried out that experiment and found time period. First time it was 2.63 seconds, second time it gave 2.56 seconds, then T3 2.42 seconds, T4 is 2.71 seconds, and T5 is 2.80 seconds. So here our true value will be the mean of all this. So we will take mean of all these time periods that we will add. Okay, I'll do it in my calculator. So this is 2.63 plus 2.56 plus 2.42 plus 2.71 plus 2.80. So the sum will be 13.12 and total observations are 5. So this will give us 2.624 seconds. Now there is one thing also, we'll change round it off to up to 2 decimal digit. This is because the significant numbers that we are keeping in our final result is also not randomly decided. It also has some rules. So these rules actually we should have discussed earlier, but because I have seen then that in lecture 2 week 2 lectures, significant figures and its rules has been discussed, so we'll also discuss this in second week. But I just want to say we should not write it like this, because all the observations have values up to 2 decimal digits only, so the final result also should have the answer up to 2 decimal digit. So our final answer should be 2 points. When we'll round it off, it would be 2.62 seconds. So here this average of time period that we have taken, this is our true value. Now if we have to calculate absolute error for this, we'll do that using this 2.62 second value, considering it to be the true value. So let's calculate this absolute error. So absolute error we have to calculate for every value that we have conducted this experiment 5 times. We got 5 different values. Now every value is deviating from this mean value, and how much is the deviation, that we'll get to know from calculating the absolute error for each of these values. So absolute error calculation will be delta t1, it will be 2.63 seconds, because I told we take mode of this, so the negative sign, it will always be positive. It will 2.63 minus 2.62, that will give 0.01 second as the absolute error for this. Similarly for delta 2, it is 2.56 minus 2.62, that will be 0.06. minus 2.62, this would be 0.20 seconds. On delta t4 is 2.71 minus 2.62, this will be I think 0.09. Yeah, this will be 0.09 seconds. And the absolute error in T5 is 2.80 minus 2.62, which will give 0.18 seconds. So these are the absolute errors in each of these readings. Now to find out relative error, if you recall relative error, I said we'll take mean of all the absolute errors and mean value. So I think we need one more blank page. So for relative error, relative error is the ratio of mean of absolute errors to the ratio of mean value or true value. So here we need to take mean of all these absolute errors. So this is 0.01, 0.06, 0.01, 0.06, 0.20, 0.09, and 0.18. These are the absolute errors. We are taking mean of it, and then mean value we have already calculated, which is 2.62 seconds. So now I'll add this 0.01 plus 0.06 plus 0.2 plus 0.09 plus 0.18. So the sum of absolute errors is 0.54, 2.62. We'll get that. And for 4 divided by 2.62. Okay, actually it is the mean of absolute errors, so we have to divide this thing by 5. We are taking mean of all the absolute errors and then the ratio of mean value. So this will be 0.54 divided by 5. It will give us 0.108 divided by 2.62. 28296. And if we have to, so this is the relative error because it's the ratio, so that's why there is no dimension. And then when we'll take percentage error, then we'll just multiply this relative error with 100. That means this much is the error, percentage error in conducting these experiments where we have found 5 different values. So this is how we calculate absolute, relative and percentage error. Now we'll see if we do some measurement and we have to add or subtract two values which have some error in them, then how the error, what we do with the error. So the rule is when two quantities are added or subtracted, the absolute error in the final result is sum of absolute errors in the individual quantities. So when two quantities, say, okay, let's do this in one example. So example question is the temperature of two bodies measured by a thermometer are T1 and T2. So these are the two different temperatures for two different bodies. And we have to calculate the temperature difference between these two temperatures and the error in that final reading. So one body's temperature T1 is 20 degrees centigrade plus minus the error in it is 0.5 degrees centigrade. Another body's temperature T2 is 50 degrees centigrade plus minus 0.5 degrees centigrade. This could be least count or something else that they have not given, but they have just told this as error in these values. Now we have to calculate the temperature difference between T1 and T2. So temperature difference, let's denote delta T, will be T2 minus T1, then 50 degree plus minus 0.5 degree. Okay. Now we have to subtract T1 from this, which is 20 plus minus 0.5. and the rule says that when we subtract or add two values, then the error always gets added. Means here the main value, the true value, we'll subtract that. 50 minus 20 will get 30 degrees, but the error always gets added. So 0.5 plus 0.5 will give us 1 degree. So this will be the final answer. Now another rule is about what happens with the error when the two quantities are multiplied or divided. So here, when two quantities are multiplied or divided, the relative error in the result is again sum of relative errors in the multipliers. Let's see with this example. Okay. So here we have voltage value given, current value given, and we have to find out percentage error in resistance. So first, what is the relation between voltage, current and resistance in a simple circuit? So voltage drop is product of current flowing and the resistance. So we can see here again we are talking about two quantities and their product. So we need to find out R, means R will be the ratio of voltage and current. So when we have to find out percentage error. So let us denote the percentage error with this small delta R, which what I mean is absolute error, mean value times 100. So percentage error we are denoting with this. Now what is the percentage error in V and what is the percentage error in I? So percentage error will be this error in the value, which is 5, and the main calculated value, which is 100, and then multiplied with 100. So this is the relative error for this voltage that has been measured. So this will be 5%. The relative error in current will be, what is the error? 0.2 amperes, and the main value is 10 multiplied by 100 again. This will give 2%. Right? And since R is ratio of V and I, that means the relative error in resistance will be like this, delta V plus delta I, because the rule says that the errors are always added. So the error in V is 5% and the error in current is 2%. So the total percentage error in resistance will be 7%. So this is how we deal with errors when we are adding two quantities, subtracting, or when we are taking them their product or their division. So based on this also, I think in your assignment there are questions. So I think now you will be able to solve them. The next thing is combination of, okay, in this there is one more thing. When we have power in any formula, for say there is some quantity x and it depends on one parameter which is a, another parameter which is b, and say it has some power also, say gamma, then what will be the relative error in this quantity x? Because for if it would be simply like product of a and b, that we have already discussed, that relative error in x will be relative error in a plus relative error in b. But what if when we have some power also? In that case it will be again sum relative error in a plus relative error in b, but this power that we have to multiply. So let's see one example. This is in general rule that if there is some quantity z which is product of a, b and division C, and they are raised to power of P, Q, R respectively. Then the relative error, or this is percentage error के लिए we'll multiply by 100. For relative error, thus the power is actually we multiply it with the relative error values. So this is how we uh, deal with the errors in this situation. So let's do one question to understand this. So this question is about Joule's law of heating. The formula is also given. As we can see, heating depends on current, resistance, and the time for which the current is flowing through that resistance. So the current is measured as 5 ampere. So the current value is given to be 5 ampere with least count of 0.2 ampere. This least count we can take as our error, because that is the least count of that instrument, so we cannot measure it more precise. So there's always will be this error of 0.2. This what we mean by whenever we write current or any value with this plus minus is like this value of current, we are measuring it to be 5 ampere, but since the instrument has least count of 0.2 ampere, so the actual value can be less than equal to 5.2 ampere, or it could be, I mean the actual value could be less than equal to this, or it could be more than equal to 4.8 ampere. So it's lying between this. Again, as we had talked about, that we are not certain, because there is a limit of capacity of this instrument to measure the current. So the current is between these two values. So this is what we want to say when we write it plus minus this error. Okay, so so current value is given 5 ampere and least count is 0.2 ampere. So we can write it like this. Then resistance value is 100 ohm given. So like we have to be careful here. 100 ohm is given. They are not measuring it. They are just taking it as it is. So there is no error they are giving here. That means the error in this value is 0. We are just taking it to be 100 ohm. Because R is not, we are not measuring here. Now next thing we are measuring is time. Time has been measured by a stopwatch which has least count of 0.3 second. So, and the time recorded is 2 minutes. So time recorded is 2 minutes and the least count in it is 0.3 seconds. So we should have all these values with the same unit, right? So 1 minute is 60 seconds, that means 2 minutes is 120 seconds, and plus minus the least count, which is 0.3 seconds. So this is the time that has been measured. Now we have to find out the percentage error in the measurement of heat. So since the heat depends on square of current and resistance and time, so the percentage error in measurement of heat will be twice the percentage error in current plus the percentage error in resistance plus the percentage error in the time that we have that has been measured. So the percentage error in current we will find out from here. So percentage error in current will be, what is the error in the value? 0.2, and the actual value measured is 5 times 100 . So this will be 4%. The next thing is relative error or percentage error in resistance. Since we had seen that resistance value was just given to us and it's not been measured, so there is no error value we have. So when we will try to calculate its percentage error, it will come out to be 0 because the error is 0. So the relative error or percentage error, this will come out to be 0. Next thing is the percentage error in time period. So here again the error is 0.3 second and the actual value is 120 second. Then we'll multiply by 100 to change it into percentage error. So yeah, what we'll find, this is 8%, this is 0, and this is okay 3 4 1 by 4. So 1 by 4 is 0.25, right? So the total error will be 8.25%. So the total error in the heat, so we are measuring in this experiment only the current, resistance, not resistance, also current and time, and based on this formula we are calculating the value of H. So value of H we will get, but the error also will be there because there is error in I and T itself. So the final value cannot be without any error, and the error in it will be 8.25%. I hope this is clear. So the correct answer in this will be 8.25%. Okay, we have more question. Physical quantity X is expressed as, this is the formula, the percentage error in measurement of A, B and C. So percentage error in measurement of A is 1%, percentage error in measurement of B is 2%, and the percentage error in measurement of C is 4%. Find the error in measurement of X. So this error they are asking, that also is percentage error because the answers are given in percentages. So because the formula is given here that X depends, K is given to be a constant, it's not being measured, so there is no error related to it, we can ignore this as well. And the remaining parameters which are being measured, we have to consider the error in those things. So this K we can ignore because it's just a constant. So the error in percentage error in measurement of X will be, let's see what this is. So this will be percentage error in A, or okay, let me simplify this first. So X is equal to A and B to the power 3, and this is in denominator, so it will be C to the power minus half. This is it's in simplified form. Now the percentage error in X will be the percentage error in A plus 3 times the percentage error in B plus half times the percentage error in C, because we know even if the variable is in product or division, the errors are always added, so that's why. So the final error value will get delta A. The error in A is 1%, the error in B is 2%, half times the error in C is 4%. So what we'll get is 2. So 9% is the total error percentage in calculating this variable X. Okay, so these were the things that you need to understand for error analysis, because there are questions based on this in your first assignment. And so this is how we deal with error and combination of error, and these were the 2 examples. So I hope you guys have understood. If you have any question, you can ask. Otherwise we can move to the next concept that was discussed, that is oscillation. So simple harmonic motion, like we had discussed a lot of oscillation, because again this is summary of what was taught in experimental physics 1. So we had discussed many types of oscillations, but here, because again the more questions were based on simple harmonic motion, pendulum, so we'll have a rough discussion on this concept. So simple harmonic motion is a special type of periodic motion in which a particle moves to and fro repeatedly about a mean or equilibrium position under a restoring force. So it's a type of periodic motion. Periodic motion we all know, like the motion of Earth around Sun is a periodic motion, or the clock, the hands of clock moving, they are also periodic because they repeat after a particular time, and always that time is also same. So after a regular interval, that motion is repeating. That's why they are called periodic. But why we are calling simple harmonic motion is a special type of periodic motion, because as in these two examples that I said, be it Earth moving around the sun or the hands of clock moving around in the sorry. So in these things, the thing is, simple harmonic motion, the particle moves to and fro repeatedly about a mean position, which doesn't happen when we are talking about sun and Earth taking elliptical path around it. Here it's not doing to and fro motion, right? It's just taking whole revolution around it. So that's why simple harmonic motion is a special type of periodic motion, because the typical example we talk about is a pendulum suspended through the point of suspension. This is called point of suspension, and it's hanging. This is its mean position. If you leave it undisturbed, it will always be in this position, and if you move it to some, or we can call it displacement, if you move it or displace it by some angle and then leave it, it will go to and fro about this mean position. So this is characteristic of a simple harmonic motion, that the motion happens about a mean position to and fro under a restoring force, and this restoring force is directly proportional to the displacement of the body, and its direction is always towards the mean position. Like first, if you take this bob of this pendulum, take it to right and then leave, although you're moving it towards right, the restoring force on it is acting towards the mean position, that is towards the opposite direction, to the direction of displacement. So this is how we define simple harmonic motion. Now this was for a pendulum. The same is applicable for this mass body system, mass spring system. Here we have a spring. One end is attached with the body, another end is attached to a rigid thing that it won't move. One is fixed, this end is fixed, and the other end is attached with a mass which we can pull or push, and accordingly the spring will compress or expand. So here again, this is the mean position when the spring is in its relaxed position, and if you pull the mass towards right, the spring will expand, and then when you release it, the restoring force which is acting in the opposite direction will bring it towards left, and for some time we'll see the mass will move to and fro about this mean position. So the same, this is also, that's why I call simple harmonic motion, because the same restoring force relation works on this also. This is, we know Hooke's law is applicable here. This is the spring constant, and this negative sign says that the restoring force is in opposite direction to the displacement, direction of displacement. So these are example of simple harmonic motion. Now we can discuss few types of oscillation. Like there is free oscillation. Free oscillation possesses constant amplitude and period without any external force to set the oscillation. In such a system, the amplitude, frequency and energy all remain constant. So free oscillation actually is kind of an ideal condition. Like if I have a pendulum, this is point of suspension, and it's suspended like this in a vacuum. Say this whole setup I have kept in a box, and I have created vacuum. Why I am emphasizing on that this is ideal condition situation, and it could happen in a vacuum, because this, what anybody would have observed, that if we'll displace this pendulum after some, initially it will do this to fro motion of course, but slowly after some time it will come to this mean position and stop. Why it stops? Because there is air resistance. The particles in the air resist this motion, and eventually the whatever the energy it had, it's spent in overcoming this resistance, and eventually it will come to a stop. So that's why free oscillation is possible, not possible in around us. It's more like an ideal condition that may happen if there is vacuum created, so that there is no air and there is no resistance. In that case, if you once disturb the system, it will, there will be no energy will just, so okay, so when the pendulum is at the mean position, all its energy in the form is in the form of kinetic energy, and when we take it to some position, here all the energy is in form of potential energy. Again, when it goes to this side to the maximum amplitude, again all the energy changes to potential energy. In between these positions, the energy is stored in some form of potential energy and some form of kinetic energy. So if there is no air resistance, then this potential energy and kinetic energy exchange will keep on happening and it will never stop. So that's why we are calling free oscillation as the ideal oscillation condition. Now the next is damped oscillation. Okay, so for a free oscillation, if with time we are talking about energy or its amplitude, it will be sinusoidal and the amplitude will remain unchanged. It will remain constant. Just depending on the direction, it's going to plus A or minus A. But it will be, the peak value will be same. Whereas when we talk about damped oscillation, so its amplitude decreases and eventually becomes zero. Why? Because here we consider the resistance offered to the oscillation because of the air or any other reason. So as we said, if the ideal situation is not there, then eventually we observe a swing or a pendulum, it comes to a halt because the energy it has, it is being spent to overcome that resistance around. So that's why this is the kind of oscillation that we observe around us, which is damped oscillation. Now third type is forced oscillation. In this, a body oscillates by being influenced by external periodic force, and this is called forced oscillation. A good example that we see around us is when a person is on a swing. A person is on a swing and her friend is in, after a certain time they are pushing the swing so that the swing keeps on moving. Otherwise, if just once you push it, after some time it will come to halt because it will get damped. But if every few minutes you will again give it a push, so eventually it will keep on moving. So this is example of forced oscillation. So these all oscillation types we had discussed in details in under experimental physics 1. So that's why we don't need to do in detail, but we'll do some examples to understand what were the basic formula dealing with simple harmonic motion. So a simple harmonic motion is usually the equation of motion for this is given by y is equal to a sine omega t. You can consider phase also. Sorry, wait. Do I have erasers? Yeah. So either it's given by a sine omega t plus phi or a cos omega t plus phi. If there is phase, we give this phi, otherwise just a sine omega t and cos omega t, as we can see here. So when we consider these two cases, is like, say if we have a pendulum and at time t is equal to 0, the displacement is, the motion is starting from this position, then we consider this a sine omega t equation, and if at t is equal to 0, the motion is starting from this extreme position, that is at t is equal to 0, the displacement is maximum, then we consider this equation. Okay, so these are the two equation of motion for simple harmonic motion. Now the question is, a particle is undergoing simple harmonic motion and the equation of motion is expressed like this. The maximum speed it achieves is 1 meter per second. Find the time it takes to reach from the mean position to half the amplitude. We have to find the time this particle takes to reach from mean position to half the amplitude. So let's first match this given equation with the standard one so that we can find out what is the value of amplitude, what is the value of frequency and other things. So if you will compare this with a sine omega t, and let's take the phase as 0 because phase is not given. So from this we can clearly see that amplitude is 0.1. Now they are talking about maximum speed it achieves is 1 meter per second. We know for oscillating pendulum that when it is at this position, mean position you can call it, or equilibrium position, its velocity is maximum and displacement is 0. Right now it is at mean position. I'll use x for displacement. I'm using x to denote the displacement. Displacement here is 0, whereas when it is at this position, the displacement is maximum and the velocity is 0. Okay, so we have to find out the time it takes to reach from the mean position to half the amplitude. So we know that the time period of oscillation is given by, the time period is, okay, first we can see. So the question is time to take reach from mean position to half the amplitude. First we will calculate here what is the angular frequency for this particle. So you know V will be V maximum. We are given it is 1 meter and we know it will be maximum when the displacement is 0. So when you will put this in this equation, so when the displacement, let's do one thing, more space now. Let me take one more slide. Just it is getting little hang. It's getting hang. Okay. I'll take one more slide here. Okay. So our equation is y is equal to a sine omega t. Now let's take derivative of this, that will be dy with respect to time. So dy by dt, I'll get a, now derivative of sine will be cos omega t, and when we'll take derivative of omega t, it will be, we'll get omega. So this will be a omega cos omega t, and we know dy by dt is velocity. Now we know what is the V maximum. So V maximum is 1 meter per second. And looking at this equation, you can see when this value can be maximum, when cos omega t is maximum, and the maximum value cos can have is +1. Because cos value takes between -1 2 plus 1. So the maximum value it can take is plus 1. And we know V maximum is 1 meter per second. Cos omega 2 maximum value can be plus 1. That means this 1 meter per second is A times omega. And A we know from this relation that A is 0.1. Thus we can find out omega is this value of velocity, which is V maximum divided by amplitude. So the omega value is what is the velocity? 1 meter per second divided by 0.1. So the value is 10 radian per second. This is our omega value. Now we need this when we want to calculate the time. So this is the omega value we have obtained, which is 10 radian per second. Now using the same equation of motion, so we have to find out what they are asking. We have to find out the time it takes to reach from the mean position, this is the mean position, to half the amplitude. This is the position where the displacement is maximum, and in between somewhere the amplitude will be half. So we have to find out the time it takes for the pendulum to reach half the amplitude position. That means the displacement we can denote with y also, x also, it's fine. So they are asking when the displacement is half of the amplitude, then how much time will it take to reach the half amplitude position. So in this equation of motion, when you will put this value, okay, you can see, so it will be half sine omega t. Now we will take sine inverse of this. Sine inverse of half will be equal to omega t. Sine inverse of half is 30 degree, right? Sine 30 gives half. So this is 30 degree and omega t. 30 degree in radian form, we can write it as pi by 6. So, and omega value we found out, which is 10 radian per second. So from this we can find out the time, and time will be pi by 6, and this will be in division. So this will be pi by 60 seconds. So the answer is pi by 60 seconds. Okay. Another question is, a particle executes a motion given by, here the motion is given by this equation. Select the wrong statement regarding this motion. So the statement is, it is a simple harmonic motion with time period pi by omega. First, we already saw what are the general form of simple harmonic motion. Let me write again. Like we say that if the equation of motion is in the form of a sine omega t or a cos omega t, then we can call it to be a simple harmonic motion. So first we will see if this form we can change it into any of these two forms to confirm if this is a simple harmonic motion. So this formula, if you see, trigonometry identity, if you recall, we have an identity which tells cos square theta minus sine square theta is cos 2 theta. Using this identity, we'll change this equation to x is equal to, amplitude will be as it is, and this cos square omega t minus sine square omega t will become cos 2 and omega t. Now if we'll compare the given equation of motion to the standard equation of motion for simple harmonic motion, we can see there is amplitude and there is angular frequency, time, so it does follow the same I mean it's similar. So we can can say that yes, this motion of this particle is executing simple harmonic motion. Now the next thing is, what is the time period in this? Here it is a simple harmonic motion. The amplitude here is, from this equation we know this is the amplitude. So this is the amplitude here. Amplitude is A. The angular frequency here is 2 omega. The angular frequency is 2 omega, and the time period will be 2 pi by this angular frequency, which will give us 2 pi divided by angular frequency is 2 omega. So the time period will be pi by omega. So the question is, which of the statements about this particle motion is wrong? So the first statement is, this motion is a simple harmonic motion with time period pi by omega. So we can see, yes, it is simple harmonic motion and the time period is pi by omega. So the first sentence is correct. The second sentence is, it is a simple harmonic motion with frequency 2 omega. So yeah, the frequency is 2 omega. So this sentence is correct as well. The third sentence is, it is a simple harmonic motion with amplitude 2a. Now here we see that clearly amplitude is a, not 2a. That means this sentence is incorrect about this particle motion. The last sentence is, it is a simple harmonic motion with displacement 0 at t is equal to pi by 2 omega. Now we'll see what is the displacement when the time is pi by 2 omega. So this is this equation we have. We'll insert the value for t is equal to pi by 2 omega. So cos 2 omega, and for at time t is equal to pi by 2 omega, when we put here, now cos pi we know is -1. So the displacement at t is equal to pi by 2 omega time, the displacement is not 0. We have -a displacement. That means this D sentence is incorrect. So the wrong statements here are statement C and D. Statement C and statement D are incorrect. Okay. Now the next question is this. We have a spring balance as shown here that reads from 0 to 50 kg. The length of scale is 20 centimeter. A body suspended from this balance. So this is another form of spring weighing balance, where we put the weight, hang the weight from here, and again depending on from this Hooke's law, the displacement will give us the measure of the weight of this body. So yeah, so a body suspended from this balance when displaced and released oscillates. Again it will oscillate, and it will be oscillating with a period of 0.6 second. What is the weight of the body? So the scale reads from 0 to 50 kg, that is the maximum weight it can show. The length of the scale is 20 centimeter. That means the maximum displacement that can happen, the maximum x value can be 20 centimeter. Maximum displacement can be 20 centimeter, and the maximum force, the maximum mass it can take is 50 kg. A body suspended from this when displaced and released oscillates with a period of 0.6 seconds. So from Hooke's law, first because we need to calculate this time period, we know time period formula is 2 pi under root mass of the body and the spring constant. So first we need to find out the spring constant. So from this Hooke's law, since the force acting on the spring will be due to mass of the body and the acceleration due to gravity, and this negative sign, as I told earlier, that it just shows the direction of force which is opposite to the direction of this displacement. So we can ignore it while calculating the values. So from this we can calculate the value of K. It will be the ratio of F by X. Maximum force we can have is this. Maximum mass that can be used for the spring balance is 50, and the acceleration due to gravity value is 9.8. Now the maximum displacement possible for this spring system is 20 centimeter. So let's convert it to, because we are dealing with kg and second, which is like SI unit, so we'll change this length from centimeter to meters. So it will become 0.2 meters. So division will be with 0.2 meters, and the answer will be, let me calculate this, 50 times 9.8 divided by 0.2 is 2450. This is in Newton. Oh, sorry, this is kg meter per second square. Yeah, so this is a kg meter per second square, and 0.2 is displacement, that is meters. This is kg per second square, restoring force. Okay, anyway, so this is 2450, or kg meter per second square is also called Newton, right? So we can either call it Newton per meter, or we can call it kg per second square also. So finally we want to calculate the time period. This we just did to find out the restoring force. Here we assumed, or we considered, the maximum weight for this balance and the maximum displacement. Using that we found out the spring constant of this spring system, and using that value, because it's a spring constant, so I mean, as the name tells, it's going to be constant for a particular spring system. It's property of that spring. So this value will be constant, and for mass we don't know, we have to find out the mass, for which the time period of oscillation is 0.6 seconds. So time period we have been given. Okay, first we need to find out the m, right? So we'll write it in terms of other parameters. So m will be t square divided by 4 pi square times, this will be in multiplication, k. So time period is 0.6 second, means 0.36 seconds. 4, and this pi square we can take 3.14 square multiplied with this spring constant that we have calculated, which is 2450 Newton per meter. So when we'll do this calculation, we'll find that the value is 2450 times 0.36 divided by 4, okay, divided by 3.14. I'm getting the value to be let me calculate this. So 3.14 times 3.14, that is 9 point this times 4. So denominator, or I'll write here, denominator is 39.4384, and the numerator will be 2450. 882. So this will be so this value of mass will be 22.36399, but we'll take up to 2 decimal digit, so we'll get 22.36. When we'll round it off, it will be 364, so we can take it to 36. This is in kg. Now this is not the final answer because we have been asked not the mass of the body but the weight of the body, and the weight we know is mass times acceleration due to gravity. So we'll multiply mass with 9.8 and then we'll get the weight of this body, for which the period of oscillation was 0.6 second. So this value will be 219 Newton approximately. So this will be the answer. So this is how we have to approach a problem. Like, we have to identify which law or which formula is applicable, what information we can extract from this, and then we have to apply it to find out what has been asked in the question. We have one more example. So here we have a spring with the spring constant. Here the spring constant is already given, which is 1200 Newton per meters, and is mounted on a horizontal table as shown here. A mass of 3 kg. So here the mass of this body is 3 kg, is attached to the free end of the spring. The mass is then pulled sideways to a distance of 2 cm. So the displacement is made up to 2 cm and then the mass is released. Now we need to find out the frequency of oscillation, the maximum acceleration of the mass, and the maximum speed of the mass. So let's do these things one by one. So we need to find out frequency, need to find out maximum acceleration, I need to find out the maximum speed of the mass. So the first formula for first part, which is frequency, you know frequency is inverse of the time period, and time period is given by 2 pi under root mass and the ratio of spring constant. So when we'll substitute here, the frequency will be 1 over 2 pi, and under the root it will be k by m. When we'll calculate this, root of k value is 1200, the spring constant, and the mass is 3 kg. So this will be right, and when we'll take square root of 400, it will be 20 divided by 2 pi, it will be 10 over pi per second, or hertz, because it's frequency. Or we can simplify this value, 10 divided by 3.14, it will be something 3.18 hertz. So this is the angular frequency of this oscillation. Now we have to move to second part. I need the slide again, extra slide. I'll take 2 slides. Yeah, so the first part is done. The next part is about maximum acceleration. In the next part, we need to calculate the maximum acceleration for this motion. So how we can find out what is the formula for acceleration? So if you recall, the equation of motion for simple harmonic motion is given by y is equal to a sine omega t. When we take derivative of it, we get velocity, right? dy by dt is velocity, and it gives us a omega cos omega t. Now when we take its derivative one more time, we get acceleration, because derivative of velocity with time gives us acceleration, which I am denoting with the small a. Now this time the equation will become, because derivative of cos is minus sine, So we'll get minus a omega sine omega t, and there will be one more omega. So finally it will be minus a omega square and sine omega t. This is the acceleration. Now if you compare this first equation with this, you can see we can rewrite this as this a sine omega t. This a and sine omega t part is actually y, and then remaining is this omega square. So what we see is acceleration is related with the displacement with this relation. This is another form of representation, and using this here we can find out the maximum acceleration. So acceleration depends on minus omega square. Again the displacement we can denote with x or y, it's fine. So we can ignore the negative sign here because it doesn't change the magnitude, it only denotes the direction of acceleration, which is opposite to the direction of displacement. Since omega is under root of k by m, when we will substitute this value here and ignore the negative sign, we will get a is equal to k by m and this displacement y. From this we can find out k, we have k is 1200, restoring spring constant is 1200, mass of the body is 3 kgs, and the displacement is 2 centimeter, right? These values are already, these details are already given. So 2 centimeter, first we'll change it to meters because everything other is in SI unit. So 2 centimeter will become 0.2 meters. No, wait, yeah, no, 0.02 meters. It will be 0.02 meters. When we'll solve this, it will be 8 meter per second square. So the acceleration for this body will be 8 meter per second square. We can remember this formula, or you can derive this acceleration relation from this basic equation of motion just by taking double derivative. Okay, so this is the acceleration. This was the second part. Now third part is what is the maximum speed of this mass. Let's do it on another slide. So third part is maximum speed. Here again we need relation between velocity and the formula we need. One thing we can do is, let's again go back to the basic equation. Okay, yeah. So the basic equation again, it was a sine omega t. Taking its derivative, we will get v is equal to a omega cos omega t, right? Now we know this identity, cos square theta plus sine square theta is equal to 1. From this cos theta, we can see that it will be 1 minus sine square theta and square root of this whole thing. The same thing we'll try to substitute here. We'll get velocity is equal to a omega and square root of 1 minus sine square omega t. Now from our first equation again we can see that sine omega t is equal to y by a. Substituting this, sorry. Oh, what's happening? Let me take eraser. Yeah. So substituting this relation of sine omega t in this equation, here we'll get V is equal to A omega, and under root it will be 1 minus sine omega t is y by a, so square of it will be y square by a square. So what we have to calculate is the maximum speed, and as I had told earlier, when this you can consider it using pendulum also, or spring mass system also, that it's easier to see here actually, that's why. But otherwise these two systems will, they both follow simple harmonic motion. It's just easier to understand from this pendulum. So when the pendulum is at the extreme position, its velocity is 0 and the displacement is maximum. When it is at this equilibrium position, its velocity is maximum and its displacement is 0. And what we have to calculate is maximum speed. So again, maximum velocity is the pendulum gets its velocity maximum when it is at mean position. Mean position means when its displacement is 0. So when the displacement is 0, I mean again you can take it as x or y also, it doesn't matter, but we are talking about displacement. So when this displacement, when displacement is 0, velocity is maximum. So velocity is maximum when amplitude omega is fine, but when y is 0, when y is 0, it will be 1 minus 0, which will give us a omega. So V maximum, this formula again, you don't need to remember every formula, but this is the way to derive these formulas. So now we needed to find this, right? So what is the amplitude here? The amplitude, what amplitude we found out? Oh. Amplitude we had found out, or okay, so yeah, sorry. Since we are talking about maximum speed, so of course it is at equilibrium, and okay, the amplitude is maximum, and the omega we know already. So V maximum is, this is omega is under root k by m, and the displacement was given to be 0.02. So okay, so this k is 1200. This I think we had calculated earlier, or anyway we will do it again. 1200 divided by mass is 3. Yeah. And this was the displacement. So we'll get 20, because this will be 400 and root of that will be 20, and then this 0.02. When we'll multiply, we will get 4 meters per second. 4 meters per second, right? It is 20 times 0.02, 0.04, sorry. 0.4 meters per second will be the answer. So this is the way to find out these formulas instead of just cramming up all these. So this was the, yeah, we have done all the parts for this question. So again, why we focused on error analysis and simple harmonic motion based questions, because these were mostly covered in your week 1 assignment. Apart from that, there were many other experiments that we had discussed, and we already had done many problems related to those experiments, which I'll quickly revise. But questions we have more focused on simple harmonic motion and error analysis because they are covered in the assignment again. Yeah. So other things that we had discussed, we had understood its theory as well as how the experiment has to be done, and then how the value is to be calculated and how its error has to be considered. So we had discussed about another kind of pendulum, which is a compound pendulum. How is it different from a simple pendulum? So the one with a string or thread and it has a bob at the other end, that is called simple pendulum. Ouch, sorry. Yeah, so this is called, okay, this is called simple pendulum. In this kind of pendulum, all the mass of the system is at one end, right? This fixed end is not part of the pendulum. The thread and the bob is the part of the pendulum, and all the mass is at one end. So when the motion is happening, all the mass is under this motion. But how this compound pendulum is different, because so compound pendulum is a rigid body which can swing in a vertical plane about some axis passing through it. Then such a system is called compound pendulum. Here the mass of the pendulum is not concentrated on any one part, but it's distributed throughout in the body. So this kind of system is called compound pendulum, and for this the time period formula and other things get changed. So yeah, it's a extended mass that oscillates freely around a horizontal axis. So in this way it's different from simple pendulum. And here we also have to consider the moment of inertia of this body, and thus the time period formula, which for simple pendulum it was 2 pi under root m by k. Here it is given by this. This is the formula for compound pendulum time period. Another kind of things about these pendulums that we had discussed was 3 modes of coupled pendulum. So when we join one simple pendulum with another simple pendulum, we can join them using a stick or a spring for more degree of freedom. Then motion or any disturbance in one pendulum gives disturbance in another. So in this way they are coupled. So they are called coupled pendulum. In this we had also discussed about in phase, out of phase. They are said to be in phase when when they are in equilibrium. This is the situation, and if we displace both of these pendulums towards right, say in this direction with the same displacement amount, then their motion will be in phase. Out of phase happens when we displace one in another direction and this second pendulum in opposite direction. The amount can be same, but the direction of displacement is different. Then these pendulums, motion of these pendulums will be called out of phase. And depending on these phase, you can check the experimental physics 1 lecture where we had discussed in detail that their frequency, their amplitude, and how the energy converts, these things change depending on how which mode they are following. And then there is resonance also, when the their motion meets the natural frequency of this coupled system. It leads to increase in the overall frequency, and that's called resonance. Under experimental physics 1, as I said, we had mostly focused on mechanical experiments and also electrical experiments. So we had understood how to calculate resistance in a circuit, or EMF, or the capacitance, reactive inductance, and how we calculate the total inductance, total resistance, or total capacitance in a circuit when we have more than one resistor, capacitor, or inductor, depending if they are connected in series or parallel or yeah, either series or there is combination of that. So these things we had covered in experimental physics 1. Then there were experiment on Young's modulus of material, which tells about elasticity of any material, which is basically ability of a material to resume its normal shape after being stretched or compressed. So we had understood its theory as well as we had done some experiments based on this. So this was about Young's modulus of material. We had also done experiments on moment of inertia of flywheel. For this experiment, this was the working formula, and then we had also understood the theory for this. Then we had also discussed about surface tension, about its theory, about how the experiment is to be done to find out the surface tension of any liquid. Again, the working formula is here, but maybe we don't need this for experimental physics to this particular module, but since we are doing a summary, so I'm just letting you know what are the experiments we had covered earlier, which if you're interested you can uh, see the already uploaded videos for this. And they were also experiment about linear expansion of metal. When metals are heated, they expand. We all know this. So that expansion also has linear relation with the original length. And so we had discussed the experiments also based on these things. These were the basic some experiments that we had done, and mainly again we focused on the simple harmonic motion here and the error analysis. So error analysis is very important. Also, one thing we should have discussed before error analysis, I think, is significant figures. When we do any measurement, how many decimal digits we should consider. It should not be random. There is a reason and rule for how many decimal digits we should consider, but that is there in week 2 lectures. So we will be discussing those things then. But meanwhile, yeah, so these were the experiments. So next week the lectures will be based on concept of significant figures and how we take care of significant figures when we add two quantities or subtract or take product. And then we'll also discuss about optical components that we see in lab. And in subsequent weeks we will be seeing the experiments based on these optical components. So yeah, this was the session. If you have any question, you can ask, or we can end today's session. Okay. Okay. Thank you, Harshada. Okay, Dr. Harshada. If there are questions, you guys can ask. Otherwise, we'll meet in next. I think this was just a summary of last uh, module, so there was nothing new as in. But from next week, I think we'll get some good new information. Yeah. Okay. Thank you for joining, and yeah. Okay. If there are no questions, I'll stop presenting and I'll. Okay, thank you. If you guys have questions, you can ask, or maybe next time also if you still have some question, because your assignment is due on 5th February. I think, yeah. So we'll have one more session before that. So if you want, you can ask questions that time as well. So I'll stop the recording now.